Welcome back to lesson 22, hypothesis test for two independent sample means. In this first example, we're going to apply our hypothesis test to answer the scenario. More importantly, I hope the scenario helps you understand what's going on with the hypothesis test and how to do it. So let's get into it. This is a fun little example that's inspired by something that's been called the Mozart effect before, which suggests that listening to Mozart music makes you smarter. But let's get into this example. Dr. Simmons is studying the effects of instrumental music on test performance. A random sample of 36 juniors from Zenmore High School, ZHS, took a practice ACT test in a quiet environment. An independent random sample of 34 ZHS juniors took the same test with instrumental music playing in the background. The mean score for the music group was 21.3 with a standard deviation of 3.1. The mean score for the quiet group was 20.6 with a standard deviation of 3.5. So let's go through this and highlight the pieces of information. And I'm going to use two different colors to represent the two different groups because we have two groups here. And that's why this is two samples. And I'll show you why. So we have a sample of 36 juniors that took the test in quiet, and those scored a mean of 20.6 and a standard deviation of 3.5. An independent random sample of 34 juniors took the test with instrumental music playing. The mean score for that group with the music playing was 21.3 and the standard deviation was 3.1. So our suspicion here, 21.3 is higher than 20.6. So the kids in this sample performed better on average on this ACT test than the kids that had it in quiet in the sample. And that's a true statement. The sample performed better under music than the sample without music. The whole bit about the hypothesis test, though, is now we're going to try to generalize these results to the population. The population being all the students taking a test with music and all the students taking the test in quiet. And that's what the mu1 and mu2 are going to be. So if we think about, let's just carry on and you'll see. Let's go ahead and attach these to symbols. So we'll just have the purple group be group 1. I'll tell you why in a second. Well, I'll tell you why right now. Let's read this last bit. Perform a hypothesis test at the 5% significance level to test the claim that instrumental music will improve performance on the test for ZHS students in general, not just a sample, but for all ZHS students taking the test. Will music help them on average? Specifically, the claim that's being tested is, we'll do this in red, test the claim that the mean ACT of juniors who take the test with music, actually we'll do this, we want a color code. The music group's purple, okay. The mean ACT of juniors who take the test with music will be higher, higher than the mean ACT score of juniors who take the test in quiet. So, for example, let's go back to the scenario. The mean score for the music group was 21.3. That's a sample mean. And we're just going to call it X bar 1. Down here, we're talking about the mean ACT score of all juniors who take the test in music. That's our mu1. So this sample mean 21.3 is an estimate of the mu1. The real mean ACT score of everybody with a ticket under music is going to be close to 21.3, but it could vary because the sample's random. And similarly, this mean score for the quiet group is 20.6. Which is an estimate of the mean score of all juniors at the high school who take the test in quiet. That's going to be our mu2. Let's go ahead and write down the info. So in the music group, if it lets me write, we had a sample of 34. That's the number of people in the sample. The mean was 21.3. The standard deviation was 3.1. And in the other group, this is where the subscripts come into play. The sample size for that group is 36. The sample sizes for the two different groups are usually pretty close. They can be the same, but they can be different. They don't have to be the same. I apologize. My little fancy little pen is really struggling today. Okay, but we'll carry on. The sample mean was 20.6 and the sample standard deviation was 3.5. And we're going to attach a little 2 to all these to say they go with group 2. Okay, so this is really easy because we're in this lesson. This is a 2-sample t-test of a mean because that's what the lesson's about. But bigger picture, you might refer to your little reference sheet here. This is a flow chart. Are we doing proportions right now? We're not. We're talking about the average or the mean score. So this is where we are today. And do we have 1 sample or 2? We actually have 2 samples. So this is where we are. So we're going to be doing a t-test of 2 independent means. So I need a new color. Two samples, they're independent samples, and we're testing means. So we want a 2-sample t-test. The requirements for these are we have both samples are random, they're independent of each other. What does independent samples mean? It means there's no overlap. So in this scenario, they're independent. Number 1, because it told you. So that's enough. But they're also independent because a person either took the test with music or without music, and not both. There's no overlap, so they're independent. And in both cases, the sample size was above 30. And so we're good. off to the hypotheses. And this is where things get interesting. The hypotheses state that the null hypothesis states that the treatment didn't work, that there's no difference. That's why it's called the null hypothesis. Null means nothing, nothing's happening. And so mathematically, what we're going to say is that the mu1, and just for this one, we're going to do all the color coding. The mu1 and the mu2 would be the same, which is a mathematical way of saying the music treatment doesn't do anything to the mean score. The mean score here of 1 would be if everybody took the test with music playing. And the mean 2 over here is saying is everybody took the test without music playing. And we have to assume that the music doesn't do anything and that those mean scores would be the same. That's our null hypothesis. The alternative hypothesis comes from, as usual, the claim being tested. And the claim that it says is that the mean score of juniors who take the test with music, that's our mu1, the way we set it up, is going to be greater than the mean score of those who take it without music. So we're hoping to show the treatment of playing instrumental music improves scores. Phew. All right, let's get on with the test. So all of these tests are the 2-samp t-test. So you go stat, over to tests. These are 1-sample z-test and t-test, even though they don't say 1-samp. And these that say 2-samp z-test are obviously 2-sample z-test, which we'll never use, number 3. And number 4 is the one we want. So you go in there and we'll enter our data. I sort of already have it in, but you would enter the sample mean for group 1, 21.3, the sample standard deviation for group 1, and the sample size for group 1. The sample mean for group 2, which is 20.6. The sample mean or sample standard deviation for group 2, which is 3.5. And the sample size for group 2, which is 36. And then we put our alternative hypothesis right here. So if you see on the screen the up and down arrow, that means you can use your up and down arrows to scroll for more options. So I just scroll to this one, and we're testing the hypothesis that mu1 is greater than mu2. So we'll choose mu1 greater than mu2 right here. This choice affects everything. So it's critical to get this part right, to get the conclusion right. And then pooled, we'll always choose no right here. And then we'll calculate. All right. Almost done here. Oops. The test statistic, since we're doing a t-test, is the t-value. And with rounding, it's going to be 887. The next one on the screen that just says p, that's always the calculator's p-value. And alpha is not ever shown on the calculator because it doesn't know, but that's our significance level as a decimal. And the rule of rejecting or failing to reject on this hypothesis test is the same as every other hypothesis test. If the p-value is low, reject the null. More specifically, if the p-value is lower than alpha, reject the null hypothesis. Is it lower? Is this lower than this? No, it's actually greater than. So when it's greater than, we fail to reject the null hypothesis, which gives us insufficient evidence for the claim. So failing to reject always goes with insufficient evidence for HA. Always goes together. And vice versa, rejecting always goes with sufficient evidence for HA. In this case, though, we have insufficient evidence, the claim that the music works or does anything. So basically, the sample means being different by 0.7 points could just be randomness in the sampling process, right? If I rearrange the students in a different sample, then we'd get different numbers. The difference wasn't strong enough to overcome the possibility that it's just random. So specifically in a sentence, at the 5% level of significance, we have insufficient evidence that, and then you can just basically restate the claim. We have insufficient evidence about the claim, and the claim here is that the mean ACT of juniors taking the test under music or with music, we'll say, doesn't improve the average test score in the general population, is what we're saying. Well, we don't know that, actually. We don't have evidence to show that it does. But the study's inconclusive. We're just going to say we don't know if the music does or doesn't. We have insufficient evidence to mean ACT of CHS juniors taking the test with music is greater than the mean ACT of ZHS. Taking the test in quiet. All right, that will conclude that particular example. I do want to mention one thing real quick, actually. Again, when we fail to reject the null hypothesis and we just say the study was inconclusive, we don't say that the music didn't do it. We just say we couldn't show that it did. So we're leaving the doors open to do a follow-up study because the results were a little bit promising. All right, that's it.